two young people. Yeah, usually we have some
Yeah,
few more
absolutely,
also.
absolutely. I mean,
So basically,
that's the
we
common goal.
try
Everybody,
to on
yes,
Saturday we just discuss science of interest to young people. Somehow we try
yeah.
to make complex things very interesting for young people. So welcome to this group. I think
Yeah,
it's very nice of you to be
thank you,
part
Pankaj,
of
and
it.
thank you, everyone. And I'm sure, like we all have the same goal to accomplish here, and we'll try our best, whatever we can do. But I'm glad, like first time I'm joining, and but I'm hearing a lot of experts here with the different industries. So I'm sure I will have my learning curve as well with you guys.
Yeah.
Thank you.
The telescope really made a very big difference to the way we think about our universe, and that's what changed many things.
Yes.
Yes,
Good,
Chatranji,
good evening.
good to see Vinay, Mrityunjay, and such beautiful children. And yes, interesting to see someone from the glass production industry also here, Rajji. I was reading about the Vortec industry where Ulas Topal CEO. I was reading his article that they are using artificial intelligence in glass production also via the manufacturing execution system. So nowadays we have AI and robotics in all areas. And yes, Vinitji has his it's from where that itself is interesting. So thank you very much for everyone joining. This is Sharad here from London. I'm a counselor, British politician and businessman, and good to see all of you here. Thank you very much.
Very nice of you, Saradji. You have come after a long time. You took a break, I think.
No, that actually I'm always here by heart. Just the thing is that I'm connected globally in a way that I have to just give time everywhere.
Yeah.
So I keep on doing so.
Okay, so Aryan and Kamya and Mrityunjay, do you have any questions to ask all these experts that we have today? You
Sir,
can ask anyone.
sir,
Yes.
I have prepared a presentation.
You want to make a presentation about what?
Stars.
About what you want to make a presentation?
Stars.
Okay, stars. So yes, you can make about say 2-3 minutes. You can make the presentation and explain to us everything, all the hard words.
Okay.
Pankaj sir,
Go ahead,
yes,
Aryan.
Wait a minute, sir. My father is presenting.
No, you are presenting or your father is.
Pankaj sir, I have just sent to you PPT sir. If you allow to share, then Aryan is justice.
You can be a presenter, right?
Yes. Aryan or Navinji, you can also present. Any person can present. Or send me, Navinji. If you send me, then I
You
will
can
also.
click on screen share, right? You can share
Yes.
screen
Sir,
share
I
and
have
then you
already
can present.
sent to you your WhatsApp number sir.
Information
Best
about
would
the
be that
stars.
the
Yes.
kid is himself or herself trying to present, right?
Hello? Your voice is not coming.
No, we can hear you. Go ahead.
Okay. Good evening, everyone. Today, I'm going to tell about stars. Stars are one of the most common and abundant in the universe. Today, I'm going to tell about their types and formation. They are made of hydrogen, helium, etc. Stars are born within the clouds of the scattered throughout most galaxies. Familiar examples of such dust cloud is the Orion Nebula. Gravity that it can kill stars in tremendous energy resisting their own gravity, but no star has an infinite supply of fuel for its nuclear reaction. When the fuel runs out of the star, stars die all over the sky. Astronomers find beautiful nebula that work gently into space by dying stars. In addition, astronomers occasionally see a new star appear in the blue brighter then fade away after a few weeks or years.
So Aryan, one question I have. You said that stars they die. Why do they die?
Sir, because they have fuel and they
Hmm.
once after they exhaust their fuel, which is
How,
hydrogen and
how,
helium,
how do they exhaust the fuel?
by nuclear reaction.
Yeah, so in a nuclear reaction, so mass is converted to energy. So the mass reduces, so the total amount of mass in the center reduces. Yeah, please go ahead. And then what happens, because the mass reduces in the center, so there is a implosion. By implosion, what we mean? It collapses because the mass has
Yes.
reduced. But that sends a shock wave, so the outer part, explodes and the inner part implodes. This is a very common phenomenon that happens in stars. So it is when the stars they explode because of the shock wave created by the implosion inside, because the mass has reduced, so the gravity is not there, so they implode. Yeah, please go ahead now.
Then fade away after a few weeks or years. You will discover what looks like a new star in the sky, a death of an aging star, only one or two each century in a galaxy. Died. The mass of a star is determining its fate. Massive stars can die in violent supernovas, but lower mass stars die quite that. To follow the evolution of stars to their graves, you can start by following the lifestyle of sunlight medium master. As it becomes a giant star, then you can see how stars end their time. A main sequence star generates its energy by nuclear fusion, reaction that combines hydrogen to make helium. The period during which the stars used hydrogen lasts long and the stars remain on the main sequence 90% of total existence. As an energy generating star, when the hydrogen is exhausted, the star begins to evolve rapidly. The nuclear reaction in a main sequence star causes fuel hydrogen to produce helium. Because the core is cooler than 100 million Kelvin, the helium cannot be used in nuclear reaction, so it's accumulate at the star center like ashes in a fireplace. Ability to generate the nuclear reaction, it does not grow. It does grow water as it contracts because it is converting gravitational energy. The rising temperature and process hydrogen just outside the core. Hydrogen that was never before hot enough to fuse hydrogen begins in a circular layer or shell around the exhausted core of a star. In that, it explains when a star loses its mass, it begins to evolve rapidly. Although the hydrogen fusion shell can force the envelope of the stars to expand. It cannot stop the contraction of the helium core because the core is not hot enough to fuse helium. Gravity squeezes it tighter and it become very small. If you were to present in the helium core of a giant star, it's done. If you represent the helium core of a giant star with a baseball, the outer envelope of the stars would be about the size of a basketball stadium. Yet the core would contain about 12% of the star's mass. When gas is compressed to such a high density, it begins to behave in astonishing ways. In this, it is written about how dense they are. To behave in astonishing ways that can affect the evolution of the star. To continue the story of a stellar evolution, we must consider the behavior of gases at extremely high densities. Normal. The pressure in a gas depends on its temperature. The hotter a gas, the faster its particle move, and the more pressure it exerts, the mass gas inside a star is ionized. So there are two kinds of particles: atomic nuclei and free electrons. Under normal conditions, the gas in stars follow the same pressure temperature laws as other gases. But if the gas is compressed to be very high densities, as in the core of a giant star, two laws of quantum mechanics comes into play, and the difference between electrons and nuclei become important. First, quantum mechanics says that the moving electrons confined in the star core can have only one certain amount of energy. Just as the electron in an atom can occupy only certain energy levels, you can think of these permitted energies as the rungs of a ladder. An electron can occupy any rung but not the spaces between. The second, called the what's okay, I would not go for the name. It says that two identical motions cannot occupy same energy levels because electrons spin in one direction, or other two electrons can occupy a single energy level. If they spin in opposite direction, that level is completely filled, and a third electron cannot enter because whenever it's dense, it will be identical to one or the other. A low density gas has a few electrons per cubic meters, so there is plenty of energy levels available. Becomes very dense, however, nearly all of the lower energy levels are occupied. In such a gas, a moving electron cannot slowing down decrease its energy, and there are no open space levels for it to drop down, so it can speed up only if it can absorb enough energy to leap to the top of the energy level where there are empty energy. When a gas is so dense that the electrons are not free to change their energy, astronomers called it degenerative matter. Though it is a gas, it has two peculiar properties that it can affect the star. First, the degenerative gas resists compression. To compress the gas, you must push against the moving electrons, and changing their motion means changing their energy. That requires tremendous efforts because you must boost them to the top of the energy ladder. That is why degenerative matter, though still a gas, is harder to compress than the toughest hardened steel. The pressure of degenerative gas does not depend on temperature. To see why, note that the pressure depends on the speed of the electrons, which cannot be changed without tremendous efforts. The temperature, however, depends on the motion of all particles in the gas, both electrons and nuclei. If you add heat to the gas, most of that energy goes to speed up the motion of the nuclei, and which move slowly and do not contribute much pressure. Only a few electrons can absorb enough energy to reach the empty energy at the top of the energy level. That means that changing the temperature of the gas has almost no effect on the pressure. These two properties of degenerative matter become important when two stars end their main sequence life. Eventually, how many stars collapse into white dwarfs, and you will discover that these tiny stars are made of degenerative matter. But long before that, the core of many earthly stars become so dense that they are degenerative, a situation that can produce a cosmic bomb. Hydrogen, I think, hydrogen fusion in main sequence stars leaves behind helium ash, which cannot fuse because the temperature is too low. Helium nuclei have a positive charge, twice that of a proton. So, to overcome the repulsion between nuclei, they must collide at very high velocities. But the temperature in the core isn't hot enough to produce those collisions. As the giant star fuses hydrogen in an expanding shell, its inner core of helium contracts and grows hotter. When the temperature of the core finally reaches 100 million Kelvin, it begins to fuse helium nuclei to make carbon.
So Aryan, I have one question. What do you mean by Kelvin?
Sir, it is a measure of temperature.
So how does it convert to centigrade? 1
Sir?
million Kelvin will be how many centigrade? Any idea?
Sir, 100. Sir, degrees.
Yes. How many centigrade? So centigrade is also one unit of temperature. Kelvin is also, you are saying, is one unit. So how many Kelvin equal to how many centigrade?
It's any relation.
I think one Celsius is equal to 273 Kelvin.
Minus 273.
Yes.
Yeah.
Very famous.
Minus.
Yes. So Kamya, have you understood everything which Aryan has said just now?
Yes, sir, I understood.
So then we'll ask you next time questions on this. So Aryan will put all the slides in that group so that others can see, Kamya can also see, and then we'll ask questions to Aryan and Kamya next time. And I think we are running short of time. Dinesh ji, I think could you tell us about your technical aspects of your work? So we have a
Are you guys able to hear me?
Happening.
hello.
Yeah, am I audible? I'm just
Yeah.
Yes, yeah, we are.
Okay. Yeah, so as I said, my technical expertise on the implementing all the project related to US healthcare. So as you guys know that here, US healthcare is not as simple as other countries, like say India or any other developed country, right? And the cost of the delivery of healthcare is also kind of too high than other country. Like if I'll say in layman term, it's like per person around $10,000 they